is still the one where they took like the like how you were typing that out in the come box there.
All right. I think we're ready. Where's my clicker? All right, running through these quickly. Let's. Oh, you have a. You want to just write it down for me? Here, I think that you guys can just be called on for this, right? Okay. So how about Andy Lee on the first one? Go ahead.
Tossing ahead of what toss a third coin is 0.5.
Right, and remember we can say that as 0.5 or 50% or 1/2, and all of those would be wonderful ways to say it. How about Ethan Chang on the next one, part B? Say it one more time, and that'd be good. 0.25, yeah, and how'd you compute it? Okay, good. So you're demonstrating you already understand the multiplication rule of probability. Wonderful. Okay. And I think everyone maybe came in knowing that. Okay, maybe not though. Nick, what about part C?
4 out of 52 or 1 out of 13.
Okay, yeah, 4 out of 52 or 1 out of 13. He said a great way to say it, which shows not only his probability knowledge but also his knowledge of the deck of cards. I hope you guys, lots of probability questions will come up here with cards. Hopefully you're familiar with the deck. If not, then you need to get out more, you know? Playing cards is fun. And then what about Alexandra, what about part D, I guess wrong, right? 4 out of 36 or 1/9. And I'm curious about how you came up with that.
Because there's 36 ways to get a sum when you roll the 2 die.
Okay.
And then there's 4 ways to roll a sum that kind.
And what are they?
1 and 3, 2 and 1, 2. Oh wait, just 2 and 2. Never mind. 3 out of 36.
All right, so 3 out of 36 on that one. All right, so we're getting progressively, we're going from like super basic and easy to somewhat interesting and hard. I love the way you approached it though, right? There are 36 outcomes, and we will talk about that distribution a little more as we go. So that was 1/12. This was 1/13. This was 1/4, and this was 1/2. Okay, to get those answers up there. Come again? Huh?
It'd be easier if you just did 1/2 times 6.
1/2 times 1/6. So tell me how you came up with that.
Because you have to be at 1, 2, or 3, and
Okay.
then that's below 4, and then there's
Okay.
like only one other thing that you can
I like how you're thinking about that. Did everyone catch how Jason just reasoned through it? Everyone hear that? That's cool. I like that. Yeah.
So I'm still confused about why it's 3 out of 6 and not 4 out of 36, because even though the twos are the same, isn't it still just as likely that they are 2?
No, it's more likely that you get a 1 and a 3 than you get a 2 and a 2. Believe it or not, right? Because you can do it in 2 ways. You can imagine you have 2 colored die, a black and a white one, right? How many ways are there to get a 1 and a 3? Well, you can get a 1 on the white die and a 3 on the black one, or you can get a 3 on the white one and a 1 on the black one, right? How many ways are there to get 2 and 2 though? Only one way, right? Yeah. So it is in fact twice as likely that we get a 1 and a 3. Disregarding order, of course. Yeah. Which is what we would intend if we were rolling dice. Okay. So hopefully you guys have already glanced at this PowerPoint, so we'll kind of zip through this and remember that it's already online. It's been there online for the last week. So I don't think, in fact, I think I'll stop to explain these, but I will not give you enough time to necessarily write this down, at least these first couple things. This is stolen, in fact, right out of the book, I think, too. So it's not like this is shouldn't be a surprise to you. This idea of a sample space is maybe even one you've heard before. Even as we discussed the warm-up, Alexandra used that kind of language, right? How many different outcomes are there that are possible for 2 dice, right? And the answer is there are 36 different outcomes on top of the dice, you know? And that would be the sample space. When she says that, she is describing the sample space. And then the event for us would be, in that example, would be rolling a sum of 4, right? And all of the outcomes that are in that event would be 1, 3, 3, 1, and 2, 2. Does that make sense? So we number, we count. Now this is key, right? That they be equally likely outcomes, right? We understand that 1, 3, 3, 1, and 2, 2 are all equally likely outcomes. They all have, each of those individually has a probability of 1 out of 36. And then we sum those up, right? How many outcomes are there? There are 3 outcomes out of 36. So that was a good example to illustrate this point. So what's the probability of getting a 5-card hand with all 4 aces? Let's do that. And when we understand this probability definition right here with equally likely outcomes, then we understand that this is really just 2 combinatorics problems from the previous week, right? I mean, don't you see it? It's 2 counting problems. How many total 5-card hands are there? We've done that one before, haven't we? It's in your notes, page back, you know, a couple pages back. Well, how many total 5-card hands are there? Forget this question for a second. Aren't there, 52 choose 5? Okay, so that's the size of our sample space. Unlike the dice problem in part D of the warm-up, that is a sample space I can't really fully picture though, right? I mean, this is enormous. It's a large sample space, but that is the size of the sample space. All hands are equally likely. How many hands now, this is another combinatorics question, have 4 aces in them? 5-card hands. How many are there? How would you build a 5-card? Let's go back to like basics. You know, if you were to build me a 5-card hand with all 4 aces, what would you do? I hand you the deck, and you do what? Yeah, Andy? Yeah, you grab the 4 aces out, isn't that what you do? And then you would do what with the other, how many other cards are there? 48 non-aces left. Okay, so you take all the aces, and then what would you do with those 48 cards? From those, you'd pick just one, right? So I mean, if you want to just write, because it's obvious, the number 48 right here, you're welcome to. Or if you want to write 48, choose 1, you could, right? Okay, that'd be fine. But the answer is, in the end, 48 divided by whatever 52 choose 5 is, right? So it's very slim, of course, but, which is what you knew maybe before you even started this problem, right? I'm going to get my calculator out too, and you can join me. I'm curious to know what the... I'm just trying to remember what the denominator is here. I don't know. Maybe we should all memorize what 52 choose 5 is off the top of our head, just because we're going to use it, you know. 5-card hands. 2, 5, 9, 8, 9, 6, 0 is what I'm getting. And this is a 48. And maybe we can reduce that, I don't know. I mean, obviously we can. But I don't, let's see, what's the DCF? We could divide both by 2. This calculator won't reduce that fraction for me. But we can at least divide by 2. We could do better maybe, I don't know. It's very small though. When you do the division here, you get something on the order of 10 to the -5th, right? So this is very slim chance. All right, what about unequally likely outcomes? Well, we can deal with that as well. And in order to even talk about, and in order to really talk about it, we need to talk about this idea of a probability distribution, okay? So we talk about in statistics or in probability theory, we think of something called a probability mass function. It's my favorite name for it. Has a physics flavor to it, and you'll see why. Unfortunately, your calculator will call it a PDF, a probability distribution function. I'm not a big fan of that because it's, anyway, for reasons that we'll go into maybe later. I prefer probability mass function, whatever. And the point is, it's a function, right? It's a function that assigns to every value in the sample space for every outcome a probability, right? Where all the outcomes, this is a special function, right? Where all the outcomes, all the f of x values, or p of x values, are between 0 and 1, and the sum of all of the p of x values is 1, right? And actually, there's one more constraint on this, but we'll ignore it for the purpose of our course. So the question is this a probability distribution function? Now notice, because these are discrete functions, and by discrete I mean they take a domain that is some kind of numbered domain here, right? We have 1, 2, 3, 4, and 5 are the only x values I'm allowing. That's pretty critical, actually, right? That you understand that that's the set of x values we're working with. Given both this, and actually this is called, sometimes it's called the support of the distribution, right? Given that these are the outcomes, and these are the probabilities, is this a probability distribution, properly defined? We can check both of these requirements. I think it's pretty clear that, without too much work, that this is satisfied, that number 1 is satisfied. You know, all of those will be, even when we do 2 to the 5th, that's 32 out of 62. So I think all the probabilities are less than 1, and certainly greater than 0. And is the sum 1? We need to check it. Are you ready? Here we go. Well, let's actually, we can add these up. What is it? 1, excuse me, 2 to the 1 over 62 plus 2 to the 2nd over 62 plus 2 to the 3rd over 62 plus 2 to the 4th over 62 plus 2 to the 5th over 62. And someone tell me what that adds up to. Does it add up to 1? I don't know. Check. Hopefully the numerators all add up to 62. And if they do, then this is in fact probability distribution, right? If we were to, there are a couple ways this could fail as a probability distribution. I had to pick this function very, very carefully, didn't I? Right? Like if I change this to a 61 in the denominator, suddenly interesting function, but not a probability mass function, right? Doesn't describe a probability distribution. You with me on that? Another way that this could fail is if I said, let x be 1, 2, 3, 4, 5, and 6, right? Then even though this is a perfectly nice function, this would no longer be a probability distribution because the support, wouldn't make it work. Yeah. William.
But to me, the denominator 63 or greater, it would still be a...
No, it wouldn't be. It wouldn't be because all the probabilities wouldn't add up to 1, right?
Oh, yeah.
Right. Yeah. Good question though. Yeah. You might have to include some more x values or something. Yeah, absolutely. Okay. So sometimes we can say a PDF, as I wanted to give this as a first example because I described it up here as a function. It's a function that takes outcomes and assigns probabilities, right? So here's a function that is like explicitly doing that. We can also sometimes, a lot of times though, we just use a table or something, right? So let's write down, maybe we can't come up with the function for this, maybe, but we can write a table for this, and we started to already, in fact, right? Alexandra already filled in one of these probabilities for us during the warm-up today, right? Part D of the warm-up. So let's do them all. Are you ready? Okay. So what is the, so we have a random variable here. I didn't say this up here, but let's say this. Okay, so this is a new idea too. I haven't maybe come out and say what a random variable is, but let x be a random variable representing the sum on 2 dice. Okay, so that's what I'm setting this up here as, and so we already figured out the probability of, for instance, that Alexandra said earlier, that x, the probability that our random variable x, the sum on 2 dice, takes on the value 4 is what we did, right? Is equal to 3 out of 36. That's the one she computed, right? Okay. Now I'd like you to do all the others too. What is the support here? What is x allowed to be? X can be this, that is the sum of the two dice could be as low as what? 2. It can be, it can certainly be 3 and 4, and what's the biggest it can be? 12, right? 6, 7, 8, 9, 10, 11. Isn't that convenient? Okay. We got. Okay. Then what is the probability of each of those things? Well, this is 3 out of 36. What about, let's go backwards. How many ways are there to get a sum of 2? Only one way. How many ways are there to get a sum of 3? Can you enumerate them? Yeah, we can get a 1 and a 2, or a 2 and a 1. I pictured this as a black and white die to help us think this through, right? And this is cool. This is helpful. It becomes a little bit hard to enumerate them as we go down this table, though, right? Because there are multiple ways to do it. One way to picture the sample space, if you haven't ever done this before, is by creating the following little table, right? Have you done this? I don't know. 1, 2, 3, 4, 5, 6. That's my row here will be the sum on the outcome on the first die. 1, 2, 3, 4, 5, 6 for the outcome on the second die. And then in this table, I'll put ordered pairs, right? Here we have 1, 1. Here we have 1, 2, 1, 3, 1, 4, 1, 5. I don't think I'll do the whole thing here, but I just want to give you the flavor. Here, this is getting a 2 on one die and a 1 on the other. Here's getting a 2 and a 2 on one on each die, etc. Okay? And so if you were to draw this table out all the way, it would be clear to us all, I think, that there are 36 total outcomes in this sample space, right? Now, which ones qualify for summing to 2? Just this one. Which ones sum to 3? This one and this one. Which ones sum to 4? We already answered these questions, but do you see it in the table? 3, 1. Do you see it in the table? There's the ones that sum to 1. There are the ones that sum to 2. Here are the ones that sum to 3. You see what's happening? Right? Keep doing this, right? You feel free to, if you have the extra time, fill in this table. And you'll see kind of some patterns emerge maybe. What is the answer to the next one? Has someone figured it out yet? Okay, so I'm beginning to see a pattern here, okay? What do you think, that without even counting, what do you think 6 is? How many ways are there to get a sum of 6? What do you think? 5 and 7. And then 8 would be 7 out of 36, right? Oh, wait, what? I mean, obviously this can't keep going on forever, right? So maybe there's something to miss. And actually, as you do this table, right, you'll keep getting these diagonals, right? But then they'll get back down here and shrink again, won't they? Okay. So yeah, this is 5 out of 36, all the way down to 12. How many ways are there to get a 12? Sum of 12. Clearly, there's only one way to do that: getting a 6 and a 6, right? And that would be represented by this last little entry right here. So these step back up this way. And this is such a useful probability distribution that, it's good to have it handy as we go forward and ask other questions. Like, once we have it in hand, asking questions like this one here is easy, right? What's the probability that we have a sum greater than 8? And this is what the previous slide was saying about unequally likely outcomes. We're going to sum the probabilities of these things. Greater than, not greater than or equal to, so greater than 8. We're talking about the outcomes 9, 10, 11, or 12 for our random variable x. So what are those, the sum of those probabilities? What is it? 10 out of 36. So the probability of x, our random variable, being greater than 8 is 10 out of 36. You see how this is done? A little bit different feel than the card problem on the previous slide, yeah.
Because the total sample size is 36.
Mm-hmm.
Should we keep it as 10 over 36?
No, this is, yeah, you want to reduce it? What is it, 5 18ths?
So should we reduce it even though the sample size is 36?
No, the only reason I didn't reduce all these fractions in the table is because I wanted to, we should verify actually that they add up to 36. We didn't do that yet. Maybe we should do that. But doing that in this form is a lot easier than having had it reduced, right? Here we go. You ready to check it? What should all the numerators add up to? If we really did it right, it should actually add up to 36, exactly. So what is 1 plus 2 is 3 plus 3 is 6 plus 4 is 10 plus 5 is 15, plus 6 is 21, 26, 30, 36. Yeah. Does it work? Yay. It should, if we did things right. Good. Yeah, right? You see how this works? I hope you're enjoying this. All right, what game is this? All right, yeah, all right. Kind of imaginary bonus points for people to that. So this is a game that you should all learn to play, along with regular card games with a 52 card deck, right? You should learn. These are good things. Get out and enjoy some games. This game is called Settlers of Catan. Yeah, that's right. And here's a zoom in on the board. You don't need to know much about the game except that you have these tiles that produce various resources, and you have these settlements, and these are cities around the edge and roads that you build. And when you settle on them, you get those resources whenever the 2 dice that are a part of this game are rolled. Right? So you would get, this is ore off of this tile, for instance, in the middle. And you would get ore, the people who live on this tile get ore whenever you get an 11 rolled on 2 dice. So how often does that happen? What's the probability that you would roll an 11? What is it? It's 2 out of 36. What's the probability that these people down here get wheat? This is a 9. How often do we roll a 9? Yeah, 4 out of 36 times according to that table. So people who play this game maybe don't recognize it, but on these, people just think, oh well, these are good, these are bad. But what are they actually? These little dots that are under the 9. It's actually the probability that space is rolled out of 36. Cool, right? So now you'll know next time you play Settlers of Catan, or if you ever do. Okay. I just think it's cool because every time I play this game, I see in front of me the distribution we just derived. I'm like, sweet, yeah. I mean, in the end, the way to win is to build lots of settlements and gather lots of resources and build stuff. You have to get 10 points or whatever. So, but you should there's a lot more rules, and you should learn. It's fun. It's a good game. Have you heard of it at least, please? Right? Okay. It's like the Monopoly of your generation. Okay. Please. Okay. It's actually just a gateway drug, by the way. Okay, it is, right. So once you learn that game, come back and consult some of us game people, and we'll give you some more deeper and more addictive and crazier, more complicated games for you to play. Yeah, I know. There's some good ones. Okay, sorry, gotta get down off of my soapbox about cool games. Okay, here's a hard distribution to derive. Let's do it together. Let's see if we can come up with this. A coin is tossed 3 times in succession. We had a warm-up problem kind of like this twice, so we said. And I'd like to derive the entire probability distribution for x, where x is the number of heads that we roll. All right? Heads will roll. Number of heads that we flip is, I guess, what I meant. Okay. Use a table, graph, and function to represent this. Let's see if we can do this. Okay. So let's see if we can come up with a table here first. Okay, this is little, sorry, and I should maybe be clear about what. Okay, so this is little x, this is big X, okay? This is the probability that x takes big X, our random variable, takes on the value little x. Okay, so what are the number of heads that we could get on 3 flips of a coin? We could get up to 3, right? What's the lowest number we could get? 0, right? So we could either get 0, 1, 2, or 3 heads. Does everyone agree with that? If x really is, big X, is the number of heads that we can get. Yes? So I think we all agree that the number of heads, x, could either be 0, 1, 2, or 3. Okay? Now, what's the probability of getting those things? What's the probability of getting no heads? That is, we get 3 tails. What's the probability of doing that? It'd be 1/2 times 1/2 times 1/2. So what is that? 1/8. Okay, beautiful. What's the probability of getting 3 heads? Also 1/8. And then what about these in the middle? What's the probability of getting 1 head? Is it 3/8? I mean, maybe you should make an argument by symmetry here. Don't you feel like this should be symmetric?
Well,
right?
And
So this is 3/8, and if you agree with that, and maybe we need to spend a little more time figuring out why we came up with 3/8. In a minute we will. How about? Then this one must be 3/8, right? Once you've agreed to those 3, why must this be 3/8? Because they have to add up to 8 out of 8, right? Okay, so let's go back and spend just one more second describing why that has to be 3/8. Why is it that the probability of flipping one head is 3/8? Can someone say more about that? Go ahead.
There's 3 spots you can flip a head. So you can flip
Okay.
it on the first time, the second time, or the third time.
Okay.
So that's 3 choose 1, which is 3.
Good. We have some choosing going on. I like that. Yeah.
That's all the stat kids, it's an or probability.
It's an or probability. Okay. Yeah.
It's one the first time, or the second time, or the third time.
Exactly. Yeah. And each one has the same probability, actually, right?
One
You can. Yeah. But this is the probability of getting the sequence head, tail, tail, or tail, head, tail, or tail, tail, head, and all of those have a probability of 1/8. Add them up, you get 3/8. Yeah, correct. Okay, so that's a little bit hard to see. You table, okay, check. Graph. Okay, this is not a very interesting graph. Are you ready? Here's little x. Here's probability that x equals little x. And then here are our distribution. Here's our distribution. 0, we'll label this in 1, 0, 1, 2, 3. 0, 1, 2, 3. And then we'll make it with points. You know, some people, yeah, you might use bars of equal width, of width 1 or something. I think that's a good idea too. We'll label this in 8s. 1, 2, 3/8. All right, and so what do we have? 1/8 and 1/8 and 3/8 and 3/8. There's a picture of this. Some people might make those with bars of equal width. That would be a fine way to do it too. I would make those bars of width 1, and the reason I would make them of width 1 is so that, why might I make them of width 1? Well, I might make them of width 1, each of them, so that the area of this picture is 1. You see it? Because the area of this rectangle is now, if each rectangle has a width of 1, then the area of this rectangle is just 1/8, and the area of this one is 3/8, 3/8, and 1/8, right? So there is actually a deep reason for me doing that. It's not just kind of like cosmetic, it looks pretty, right? Okay, there, I'm making each width of those at 1. Okay, and then can we come up with this actual function? I mean, certainly the domain will be 0, 1, 2, 3. Got that figured out. But can we come up with a function? The denominator, I think I figured out. It's 8. All right. Can we come up with a function that gives me the numerator, though, up top? And what is it? I mean, I feel like some of you might have figured it out. Right? It's 3 choose. This is the hard part. I don't know if I'd have you reproduce this, but it's 3. How many ways are there? So there are how many ways total to flip 3 coins down the bottom? 8, right? That's our sample space, right? If you were to write out, that's so few, in fact, we could actually write it all out, couldn't we? I wrote 3 of them here. You could write the other 5 down too. There are only 8 ways to flip 3 coins, aren't there? So write them all out and you'll see, okay? So that makes sense. How many ways are there in that sample space that you wrote out to choose 2 to be heads? Well, you have 3 flips, right? And you want to choose 2 of them to be heads, right? Does it make sense that this should be 3 choose X? How many ways are there to choose 0 of the 3 flips to be heads? Wouldn't it be 1 way? That's 3 choose 0 ways? Pretty cool, right? Okay. 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3 add up to 2 to the 3rd, right? Did you know that? All right. Anyway, so this is cool. I don't know. I mean, anyway, I think this is a good discussion. This is a discussion that you haven't ever had with probability before, and I think this is good. Are you liking this? Okay. I want to make sure you're seeing how we can think about probability in like a bigger way than maybe you've done before. Let's throw this up here at least. We're winding down the amount of time we have today, but that's okay. It's clear to me, the reason I say let's throw this up here as well, because it's clear to me that you basically already understand this. In fact, we've already been using it in the warm-up, and then just now, again, people were like, oh, it's 1/2 times 1/2 times 1/2. Right? You know already, maybe, that you can find the probability of 2 events provided, and we haven't yet defined this, but provided that they're independent, one thing doesn't affect the other, and we'll say more about that later, then the probability of one happening followed by the other is P of A times P of B. And are you okay with this? Meaning and? That's a cap, which stands for what set operation? Intersection, right? This is the intersection of these two events. What's the probability that both occur, that A and B occur, right? Okay? So I think I got two here that are both equally boring problems. Take a look at them. Verify that they are in fact boring. And okay. And then compute the answer using this boring rule. Well, it's not that boring, actually. Pretty more, maybe more profound than we think. Reading the question will take longer than solving it, right? I hope. Maybe I'm overselling. And this first, I like both these examples, even though they're kind of silly and boring, because the first example, it's clearly true that these are independent processes, right? I'm picking from jar A with this hand and jar B with this hand, and nary the two shall meet, right? Like this hand, the left and the right hand don't know what each other are doing, right? The fact that I picked a white marble out of this jar, ooh, that's going to really affect the outcome of my probability of picking a white marble out of the second jar or something. No. All right, so what is the probability that this would happen? What are we trying to do? What's the probability that they're both black? How are we computing that? Actually, I have to think through this too. It's 40 out of 100, is that right? That's the probability of jar A, getting a black one from jar A, times jar B has 5 out of 25 total. Is this okay?
Yeah.
And then whatever that comes out to, right? We could work it out. What is it? 2/25? Someone verify that that's right. I'm just trusting Ethan, but I don't know if that's wise.
1/5 times 2/5.
1/5 times 2/5. There you go. Okay, perfect. Perfect. There we go. 2/25. And I think, like I said, I like both these examples, even though they're a little bit silly, because the first one is pretty obvious that they're independent, whereas the second one, it's not obvious. And so I have to tell you, right? If I didn't say that, this would not actually be obvious, right?
Because there might be like a deal where you get
Yeah,
free
absolutely. There might be like the fact that I know that you got Frosty might be like very significant in understanding whether or not you got fries or a burger rather.